How are we doing today? Today we're continuing on in bonding, specifically with intermolecular forces of attraction, abbreviated as IMFs, and then electrical conductivity, when things conduct electricity or what gives things the ability to conduct electricity. So remember, IMFs are intermolecular forces, so the forces between. I mean, they're called bonds, but not really. They're really attractions due to charged particles being on the outside. All right. Anyways, first things first, you have a bell ringer. So you have to type the because but so statement. So water contains hydrogen bonds because. All right. So water contains hydrogen bonds because it contains hydrogen bonded to oxygen, but the electronegativity difference is less than 2. So that creates a polar molecule, which creates the hydrogen bond. It wasn't my best because but so statement, but it works. All right. Let's see if you guys can what you guys can come up with on yours. Just kind of putting your thoughts to paper. All right. There's lots of ways to go with it. All right, so today, intermolecular forces of attraction. Last class, we talked about hydrogen bonding, all right, which is really an attraction or a force between particles. And realistically, the molecules that we have to worry about hydrogen bonding are water and ammonia. Hydrogen bonds are a dipole-dipole interaction, so we're going to continue on generically with those, which should be pretty easy. Molecule ion, just introducing them. It's going to be more in solution chemistry, which is a unit coming up. And then we'll talk about dispersion forces really, really quickly. All right, so we have our 3 main bond types, and then we have our intermolecular forces. So today is an intermolecular force day, and then we will wrap up with conductivity at the end. All right, so first things first, intermolecular force, hydrogen bond. So if you look here, you got ammonia molecules. And I'm going to kind of try to pause here and wait for that bottom thing to go away. But if you look here, ammonia is NH3. So you got a blue N and 3 gray H's. All right, so what we have here is we have 4 ammonia molecules. And you can see that they've drawn in 3 hydrogen bonds, which are like the green dotted bracelet type things. All right, and that's an attraction between molecules where the positive and negatives come near each other. There could be more, all right, but this is just trying to simplify the molecule as much as possible, or the drawing as much as possible. All right, but hydrogen bonding, to review, are only found in polar molecules. All right, and it has to be between a hydrogen and a neighboring highly electronegative element. Remember, those highly electronegative elements are nitrogen, oxygen, and fluorine. All right. People who took living environment, that's why I put this up here. All right. If you can recognize this as being DNA, all right, you got your 2 strands, and then they're joined together in the middle. The bases are joined together by hydrogen bonds. Your living environment teacher may have talked about that last year. If you haven't taken living environment or biology, when you get to it next year, it'll make sense to you. All right. Remember, you got the double-stranded DNA here. So strand 1, strand 2. This is not twisted. All right, it's kind of flattened out so you can see things. You got your ATs and GCs and such. Should ring a bell for people who did take that. But anyways, dipole-dipole force is basically similar to a hydrogen bond. It's just not as strong as a hydrogen bond. All right, it's an attractive force between polar molecules. All right, so if you look here, this is just a representation of a polar molecule or a dipole. Remember, dipole, positive side, negative side. Positive side, negative side. This is a solid, all right, because it's a nice regular repeating pattern. All right. So where you get the dipole-dipole force or the attraction is between the molecules here. So when I pop these up here, you get this attraction between a positive in one molecule and the neighboring negative. And we could actually go this way too. I didn't think to put circles on here for this, but we can go positive to negative here as well. So you're going to end up with kind of a little bit more force holding it together because you can create 2 dipole-dipole forces when it's arranged as a solid. Okay, that's why it does take so much energy usually to melt things or the heat of fusion. Okay, molecule ion attraction. So it sounds fancy, sounds hard. If you break down the terms, it's really not that bad. Molecule, remember, means a covalently bonded substance. Ion is an ion, it's a charged particle. So if we look at these pictures down here, both these pictures, this is just like before it starts and this is as it's going. You have a particle of salt, sodium chloride. So it's a solid, it's got this nice pattern. Now you can remember you got those interactions, the dipole-dipole interactions going on within the salt. All right, but the molecule ion is going to be when the salt reacts with the water. All right, so water is the molecule here. All right, it's the covalently bonded substance. And remember, it's a polar substance, so it does have a positive and negative side. So what happens is the water molecules will kind of pick at the outside, so to speak. So think of it, you take a big chunk of salt, you throw it into water. If it's a big solid piece of salt, it's going to take some time for it to dissolve because it takes some time for the water molecules to kind of react with the ions that are on the outside. It can only get to the outside ions each time. So here the the oxygen side of the water molecule is going to attack the positive sodium, and the hydrogen side is going to attack the negative chlorine. All right, and what happens, you can see like here, it pulls it off, and then other water molecules will surround it. And this is actually the act of dissolving. It doesn't react and change the sodium. It just completely encapsulates the sodium or surrounds the sodium so that it's now just surrounded by water and you don't see it anymore. Same thing happens with the chlorine, except for the water molecules oriented in a flipped progression. All right, you got the negative chlorine that's going to be attracted to the positive side of the hydrogen. So what you end up with here is the molecule of water is attracted to the negative ion of chlorine in this one, or the molecule of water is attracted to the positive ion of sodium in here. So that's what it means by molecule ion attraction. It's the attraction between ions and molecules of water in a solution. All right, and we'll come back to this later on in the year when we talk about solution chemistry. All right, but I do introduce it now because it really has to do with bonding or intermolecular forces. All right, because it makes a lot of sense right now because you can kind of understand the bonding and what's going on. And then what's going to happen here? So once you pull off these two particles, the sodium and the chlorine, the water is going to attack the next available one. And it goes on all over the place. We simplify this drawing down so you can kind of see what's going on. But that's what we call a molecule ion attraction. So it's between a water molecule and usually something dissolving. You can also get it with ammonia as well. Water and ammonia work pretty well together, all right, as similar objects. All right, dispersion forces. All right, you can call them, these can be van der Waals forces or London dispersion forces. There's lots of different names for them. But I think this little GIF here does a pretty good job of explaining what's going on. So if you see you got two neons, which normally aren't charged particles. All right, neon is noble gas over there. They have full valence shells, and these work in noble gases. All right, when they do get near each other, what happens is just by chance, the electrons will orient on one side of the atom versus the other. So when they're on the side, one side, it's going to be negative. The side that they vacate is going to be the positive. And then that can cause a neighboring neon to do the same thing. This side here being negative can cause this side to push the electrons away and become positive. And then what you end up having, in like almost all intermolecular forces, it's an attraction between the positives and the negatives. All right, you get that positive and negative charge in there. So this is a very weak intermolecular force between non-polar molecules. So generally, these are non-polar molecules, and usually it's just group 18 or the noble gases. All right, and then when they get to each other, they can kind of shift the electrons. It starts off by chance, and then the charge exists, and it can happen there. The bigger the atom, the greater the strength of the dispersion force. All right, so what happens here is you take a non-polar atom, and it forms a temporary polarity, just by chance at first, and then it happens. All right, but the bigger the molecule, the stronger the force, because you're going to have more electrons. The bigger the molecule, you're going to have more electrons that are going to shift to one side or the other. So you can start out, so you look at your group 18 elements, helium being the smallest, and moving up to, we stop at krypton. All right, krypton's going to have the strongest dispersion force, just because it has more electrons that can shift. Okay. All right. So that wraps up. That's literally, like I said, I wasn't going to spend a lot of time on these intermolecular forces, but it's pretty simple to understand. The retaining, remembering part of it becomes a little bit of a challenge. All right. So some just general terms. And once again, I introduced these now. This goes along with solution chemistry, dissociation. If you've ever heard of dissociation in chemistry, it's the process of splitting an ion into its ions. An ionic compound into its ion. So taking sodium chloride and making a sodium ion and a chloride ion. So that's the ability to break apart, how easily you break apart. Electrolytes, I do like to talk a lot about electrolytes. I'm not going to talk a lot about electrolytes right now. Electrolytes, strict definition, is a substance that can conduct electricity when in solution. All right, so if you look at the definition there, it's a substance containing free ions that makes the substance electrically conductive. All right, I talk about electrolytes in sports drinks, Gatorade, Powerade, Pedialyte, vitamin water. All right, they're added there not for energy. A lot of people think the electrolytes are added to those for energy. They're not. They're added to those drinks to help your body rehydrate quicker. All right, a very, very low concentration salt solution. People who don't drink Gatorade, when they drink it, it does taste salty. And that salt is there to help your body hydrate quicker. All right. And it's the right amount of salt. Too much salt and can dehydrate your body. So it's kind of a nice little balance in there. So I don't want you to go home making your own salt water and drinking it. Not that anybody would. All right. But I do like to talk about pickle juice. A lot of people have heard about pickle juice being used by athletes or people who work out heavily to hydrate themselves. It does help. There's a lot of research on it. And realistically, the research boils down to the fact that people don't like the taste of pickle juice in their mouth when they're working out, so it causes them to drink more. It triggers their or their thirst center in their brain to drink, and the taste in their mouth. They want to get rid of it, so they will drink, even when they normally wouldn't want to drink. All right, but that's just a quick little discussion on electrolytes, because now we're going to talk about things conducting electricity, and that has to do with electrolytes. Okay, all right. So when does something conduct electricity? Something conducts electricity when it has freely moving charged particles. All right, so it's got to have a charged particle, which can either be an electron or an ion. And those charged particles have to have the ability to be able to move around. All right, if you don't have both of those criteria, something will not conduct electricity. All right, particles can be ions, they can be electrons, as long as they can move. And being able to move or being mobile is huge. All right, that gives one thing the ability to conduct electricity, and another thing the ability not to conduct electricity. All right, and I want to break a misnomer out there, or a myth. Water does not conduct electricity. All right, if you have pure water, nothing else in it, it cannot conduct electricity because it's covalently bonded. If it's got stuff dissolved in it, which it normally does, that allows it to conduct electricity. All right, so like a pool would have things dissolved into it, and chemicals, sweat, stuff like that. Lakes, the same thing. So they can conduct electricity. That's why electrical storms are dangerous for being in water bodies. All right, if it was just water, wouldn't have anything to do with it. All right, wouldn't have to worry about anything. All right, so metals. Why do metals have the ability to conduct electricity? They will conduct electricity in solid, liquid, or realistically in gaseous form as well. We're not really familiar, you guys, nor me per se, with metals as a gas, so I really don't talk about them. But they will conduct electricity in either phase or any phase because they contain freely moving electrons. All right, if you think back to metallically bonded things, there's that catchphrase of sea of electrons. All right, so you have the kernel. So here are the kernels right here, all right, which is the metal ion, the positive side of it. And then all their electrons have the ability to move all around. They're not locked into place onto one particular atom. All right, so that gives metals the ability to conduct electricity and conduct heat and be shiny and be malleable and be ductile and things like that. All right, but when we're talking about electricity, that's why metals traditionally are used for wires. All right, because they're such good conductors. There are some metals that are better than others at conducting, and some metals that are better than others due to other properties like their bendability, like they bend, they don't break, and things like that. All right, and cost comes into play as well. All right, so metals, metallically bonded things will always conduct electricity. All right, we're going to talk about ionic substances. Ionic substances, all right, in different phases do different things. So we'll first start off with solid. So first of all, let me say ionic substances, in theory, should always conduct electricity because they have ions. But that's not the case, because the second part of being able to conduct electricity is having the ability for those ions to move. All right, so oops, I don't know what I did there. As a solid, all right, it does have charged particles. So if you look at this drawing right here, it does have charged particles. All right, but because it's a solid, these ions or these charges are locked into position, so they're not free moving. So an ionic solid, so if you take a solid hunk of salt and try to pass electricity through it, won't work, because the ions don't have the ability to move. These things are locked in place, so it can't transmit the electrical pulse. All right, so the ions are locked in place. As a liquid, things change. All right, as a liquid, things change. All right, because now the ions aren't locked into place, so they do have the ability to. I don't know why it says does not. It should say does conduct electricity. I apologize about that. I'm not going to correct it. Can I correct it? I don't know if I can. Yeah, I'm going to correct it. Let's see. Can I do this quickly? Exit to does. I don't know why I have not on there. I don't know what happened there. All right. So liquid, when melted, can conduct electricity, so it does conduct electricity. Solutions, all right, in solution, when it dissolves, the ions will separate out. All right, so you can see the positive ions, negative ions start to separate out. So they do have the ability to conduct electricity as well. All right, so in a solid, they're locked in place, so no ability to conduct electricity. Liquid, solution, gases. All right, and I come back to that term dissociate. The solution has the better it dissociates or breaks apart, the better conductor it is. If we were going to do a lab on this, which it's not going to work to do it virtually, we would talk about that a little bit more into detail. All right, but if you look here, this is that same diagram. You got some molecule, which is probably water, even though it's a different color. All right, is dissolving these particles. You see the green one getting pulled off, the gray one getting pulled off here. So if it breaks apart easily, it will conduct electricity better because it'll make more ions. If it stays together as a solid a little bit longer, then it's not going to conduct electricity as well. All right, so here what I have, I'm going to play a quick little video. This actually does a pretty good job, and this is in lieu of our lab for conductivity. Some people will like this, some people won't. It's just a different way of explaining it, and I'll be quiet. Oops, I thought that would play it. Struggling today. There we go.
Conductivity and ionic compounds. Well, Dr. Atkinson is approaching the test shed, if you will. FMCP, freely moving charged particles. Anything with freely moving charged particles will conduct electricity. I see an ionic crystal lattice in the center there, and that seems to be about to be attached to a positive and a negative terminal of a power source. Maybe you'll use a battery or a regular power source in the lab. I'm using a massive power source. Positive ions here, negative ions there in the lattice. And if electricity flows, then these lights should come on, indicating a conductor. Alrighty, let's plug it in. Attach the positive electrode there, and the negative electrode to the other side of the crystal lattice. This could be sodium chloride or potassium bromide. Pretty much anything that's made of a metal and a non-metal will be an ionic bond. You know, the solid does not conduct electricity. And the reason is it because it doesn't contain freely moving charged particles. The ionic solid, they're not freely moving those ions. They're locked in position. But, using my mind, I can heat up the solid now. If I heat up an ionic solid, and it has to be really hot because those bonds are really strong. Where did I go? Then the ions will actually split apart from the lattice and become a liquid. So you have, for example, liquid salt at very, very high temperatures to make that happen because the bonds are very, very strong. Now the negative ions are going to be attracted to the positive electrode. And when they get there, they're going to drop off electrons. So the negative ions drop electrons off at the positive electrode. And the positive ion, in red, receive electrons from the negative electrode. So if electrons are being dropped off at one side and received at the other, well, that's a circuit. Electricity is passing around the circuit. The lights come on. Okay, ions are the charge carriers in the middle, but the circuit is complete. I'll turn the lights off. So liquefied or melted, same thing, ionic compounds conduct electricity. Well, there's another way you can cause ionic compounds to be freely moving charged particles, and that is to dissolve them in water. So if I was to shoot water at an ionic crystal, what will happen is it will also produce freely moving charged particles. You can think of dissolving salt in water. Salty water also conducts electricity. The red lights are still on. You just fix the electrodes here. So solid ionic compound is an insulator, doesn't conduct. but you can make it conduct electricity by melting it or dissolving in water. What happens if I attach those electrodes to my power source? Let's see what happens. Looks like a huge antenna. What could go wrong? Dr. Atkinson fearlessly makes the circuit parallel. Nothing. It's the colour of bromine, red-brown. You need to know that. Looks quite safe. No problem. He survives another day.
All right.
Conductivity and ionic compounds.
So that's just kind of another way of explaining it, or more in detail a little bit. Some people like the little graphics or whatever. But so we talked about metallically bonded things, they can conduct electricity. Ionically bonded things can conduct electricity when they're not a solid. Covalent compounds, generally speaking, can never conduct electricity. All right. They don't have ions and they don't have electrons that can move around. So they don't have any of the criteria to be able to conduct electricity. So as a solid, they won't conduct electricity because they have no charged particles. As a liquid, they won't conduct electricity because they have no charged particles. In solution, now for us, for our level of chemistry, they won't conduct electricity. But there are two types of organic compounds we'll talk about during organic chemistry that can conduct electricity because they do form ions. But for right now, covalents do not conduct electricity. All right. This guy's got another quick little thing. Let me just see what's next before I. All right. I'll wrap up with this. Yeah, we'll show it. I'm just gonna skip through a couple things.
So if covalent compounds are insulators and water is a covalent compound, how comes throwing a toaster into a bath of water is considered dangerous? Well, generally, covalent compounds are insulators. They're non-conductors of electricity. Since their valence electrons, their outer electrons, are tightly bound within the covalent bonds, so they can't move. That's the IB answer. It's not quite true, but it's true enough for IB. So for any substance to conduct electricity, there must be freely moving charged particles. And essentially, those break down into two things: electrons that are mobile or ions. Now, there are no ions present. This is covalent bonding, so it must be electrons. So the electrons cannot move around in a circuit because they're trapped in lone or bonded pairs. So a recap: there are two types of covalent compound: the macromolecule.
So we're not going to talk about the macro or the micro. I'm just going to go to the end, go back to the dude with the bathtub.
So back to our mystery. Well, you don't bath in 100% distilled deionized water. There are ions present in the water, perhaps from your sweat or naturally occurring in the water supply. Don't try this at home.
Okay, so that wraps up. So just kind of summarize, covalent compounds do not conduct electricity for us right now. All right, they don't have ions, they don't have freely moving charged particles. All right, and that wraps up today. We'll see you next time.